Natural computing is a field of utilizing knowledge of functionalities in biological systems to solve computational problems. One of its subfields utilizes the current understanding of neurology and neuroscience, especially regarding learning, in order to develop efficient and effective algorithms. By exploring the similarities between some of the proposed algorithms, we attempt to determine how such systems emerged while taking phase transitions of random networks and evolution into consideration. In order to understand the internal structure and functions of biological or physical systems, one would need to create simplified models that mimic phenomena detected via measurements. In order to comprehend and model the human brain, phenomena such as abstraction of sensory inputs, inverse kinematics, and decision-making should be taken into consideration. Artificial neural networks, or ANNs, are a subfield of problem-solving algorithms that attempt to model the functionalities of neurons in the brain. There are mainly three types, usually referred to as generations, of ANN models. First-generation models are known as perceptrons, where each neuron J is defined by Yj equals phi of the summation of Wij xi, where Yj is the output of the neuron, phi is the activation function, and Wij is the weight for each input, xi. The input, synaptic weight, and output are defined as floating points. ANNs, whose parameters are updated using evolutionary algorithms, can be classified into this type, since it only requires generation of networks with random parameters or architectures for training. Second-generation models add backpropagation, a feedback loop based on Hebbian learning, which updates the weights depending on the frequency of the usage of the synapses. Gradient descent is an example of such method to train such networks to solve specific problems. Third-generation models, also known as spiking neural networks, replace the inputs and outputs of neurons with pulses. For simplicity, we'll refer to pulses as a Boolean value. Hopfield-Tank-Amari network, or simply Hopfield network, and Boltzmann machine are some of the more famous examples. We focus on second-generation ANNs, which successfully replicate simplified function of trial and error process of learning seen in the brain. Second-generation ANNs, in particular, are shown to produce results with high accuracy and are implemented into software applications for functionalities such as image and speak recognition and robotic control. The learning method of ANNs can vary depending on the algorithms used. For example, evolutionary algorithms can be used on perceptrons, while gradient descent would not work on ANNs without backpropagation. Here we take two notable algorithms, gradient descent and Cohen's self-organizing map, or SOM, both of which specifically attempt to replicate biological neural networks and attempt to compare their functionalities in order to understand their similarities in structure of the networks. Gradient descent is a supervised learning algorithm, or algorithms that attempt to match the output of a function to a certain set of values, that updates parameters of ANNs by utilizing their gradients and determining the direction of the downward slope in the fitness landscape, or the continuous space in which the value of error is determined per any weight values. Whether such backpropagation algorithms are seen in nature is still up for debate. However, we would still take this algorithm into consideration due to the existence of biological neural networks with similar functions. During feed-forward, the aforementioned function for determining the output of neurons in a perceptron is used. Yj equals phi of the summation of Wij xi, where sigmoid hyperbolic tangent, rectified linear unit, and softmax functions are used for defining phi. During backpropagation, partial derivatives of the error for each weight values are determined, where Cj is the correct value of the output of the neural network, and minimum square loss function is used for the error Cj minus Yj, and added onto the weight. The calculated gradient may be weighted with a hyperparameter in between 0 and 1 called learning rate before updating the weights. On the other hand, SOM is an unsupervised learning algorithm, or algorithms that attempts to learn the abstractions of a given data as clusters, that models the mapping of sensory input onto the cerebral cortex of the brain using the following equation, where psi is the activation function that selects one or a set of wij that is closest in value to xi, making inverse rectified linear unit and inverse sigmoid as its valid choices. This is referred to as competitive learning. In order to update the parameters, the error wij minus xi weighted with learning rate is added onto the weights. In practice, second-generation ANNs are used to learn with these two methods, or as you may recall, have input and output values as floating points. In order to compare functionalities of ANNs between those that incorporate gradient descent and SOM, it would be useful to define functions of neurons in a more abstract manner for both feed-forward and feedback. Gradient descent can be defined as the following for feed-forward and the following for feedback or back propagation. SOM, on the other hand, can be defined as the following for feed-forward and the following for feedback, where Yj indicates whether neuron J was activated by the operation. We put emphasis on the fact that FFGD of X, FBGD of Cj and Yj, FFSOM of X, and FBSOM of X and Yj can all be defined by some form of nonlinear function. Considering this, it is possible to make the assumption that the evolution of neural networks, or even the emergence of neurons themselves, are based on logic units that are capable of conducting all four of these functions. By comparing the form of the functions, we can define a function that the basis logic unit J would have possessed. The feed-forward function is ff asterisk of x, and the feedback function is fb asterisk of x, yj, and cj. If we consider recurrent neural networks as well, where some of the neurons use their own output signals as input, the feed-forward function becomes ff asterisk x, yj. Additionally, if we consider that recurrent neural networks may be Turing complete, ff asterisk of x and yj may also be Turing complete. This functionality may be similar to those seen in cellular automata. We will now refer to the logic unit that consists of ff asterisk of x and yj and fb asterisk of x, yj, and cj as unit neurons. During the emergence of life, diverse molecules form the network, which produce clusters that are autocatalytic and self-sustaining. Such networks, now known in the form of DNA strands, can also form a network which produce different types of proteins needed to form a cell, one of which would presumably be unit neurons. In order for unit neurons to have emerged, there would have been a specific scheme within a DNA strand that dictates the formation of such through evolution. Above this, the unit neurons would have had to develop specific functions, ff asterisk x, yj, and fb asterisk x, yj, and cj, that would conduct the aforementioned feed-forward, backpropagation, and competitive learning. In order for the unit neurons to form a neural network with synchronized units, it would have developed a network similar to Watt-Strogat's model or small world network, which have been seen in biological neural networks. Each of the emergence of these concepts go through phase transitions, as Kaufman has stated on random graphs, which would have increased the complexity or hindered the development of intelligent organisms. This may explain the lack of intelligent creatures in the universe, as suggested in the Great Filter hypothesis. We have explored the possibility of the existence of unit neurons by obtaining abstract forms of models of the brain. The possibility that such unit neurons would have possessed Turing-complete functionalities, the number of phase transitions that would have occurred for it to form into a neural network. Further development in neurological modeling is expected, especially in the open question of activation of central pattern generators and its relationship with the cerebral cortex. I have recently released an open source neural network library which takes the idea of unit neurons into consideration. Unfortunately, I would not be able to take a large part in this development due to personal and medical reasons at the moment. However, I certainly will be on a lookout for merge requests, so please feel free to hop in. Thank you so much for your attention.